This is our glider report for AE 1601. The assignment was to design, build, and test a small glider and build on the knowledge we learned in 1601, as well as working with teammates, collaborating with peers, and this assignment is graded on a successful build, successful flight test, and the report. The requirements were that it had to be a hand-thrown glider flying a minimum of 20 feet. It also had to fit in a 16 by 16 inch box and stay intact during the flight, meaning no disintegration upon landing. It was prohibited to use a remote or automatic control of the wings, and it must be a glider made primarily of balsa wood and have at least one iteration on design. The measures of success are a video of the glider being thrown at least 20 feet, a smooth and stable flight, being structurally sound and light enough to fly past 20 feet. Some design alternatives we considered were rectangular wings, meaning the width and length are consistent across the entire surface, having a low aspect ratio, which ensures stability. The pros of this rectangular wings are they're easy to build and they have a predictable performance. The cons are they're less efficient and have a shorter glide distance. Tapered wings was another alternative, meaning a wider chord near the root that narrows toward the tip. And the pros of this are they reduce drag and improve lift distribution, have longer and more stable flights, but the cons are there's a potential for a weight imbalance and they're more complex to build. A V-tail was also another alternative, and that replaces the horizontal and vertical stabilizers with two surfaces arranged in a V shape. The pros of this are their reduced drag and lower weight. The cons are there's a potential for instability. The best design, and the one we landed on, was elliptical wings, which maximize aerodynamic efficiency, minimize drag, and are ideal for long, smooth glides, and they balance lift distribution. We also landed on a typical horizontal and vertical stabilizer. So sizing and initial concepts, it had to fit in the 16 by 16 inch box, and we were also limited by the amount of balsa wood given. Our initial design choices were the wings having a width of 2 inches and a length of 14 inches and a dihedral angle of 5 degrees, and the horizontal stabilizer having an anhedral angle of 5 degrees. For the initial prototype, we used cardboard, and we tested the location of wings, the amount of mass to add, and the location of that mass. This prototype was not very stable, and the cardboard was difficult to work with, and it was flimsy. And this prototype, when we test flew it, it didn't fly in a straight line and would often nose dive dramatically. So then we manufactured with the balsa wood components, and we taped the wings on in different locations to find the optimal design. With the balsa wood, it flew much stabler, and it flew past 20 feet and stayed intact. The aspects for improvement are the location of the wings and varying the mass components and also varying the location of the ballasts. And some design changes we planned on were iterating on the location of the wings, so we flew the gliders at different wing locations and found which made the flight most stable. And we also iterated on the mass components, and that allowed us to find the best combination and the right combination for the best and most stable flight. The final design we landed on was elliptical wings, and the wings a half an inch forward of the center of gravity. The ballasts were 6 grams of Play-Doh on the nose, 3 grams of Play-Doh in the middle of the wings, and 2 grams behind the wings. And here is a glider drawing to scale and the final balsa wood glider.
The center of gravity is located 1 11/16 inches behind the leading edge of the wing. Thus, the center of gravity is 1 3/16 inches behind the quarter chord. Considering that the glider performed a steady level flight, the coefficient of lift can be calculated independently from the launch angle of attack as 2 times the weight of a glider over the product of the free stream air density, which in this case is the air density at sea level, the estimated velocity squared, and the wing planform area. The coefficient of lift for a glider is estimated to be 0.63, which is within acceptable range for a small glider flying at low angle of attack. The induced drag coefficient is found to be approximately equal to 0.016 by taking the square of the lift coefficient and dividing it by the product of pi, the Oswald efficiency factor, and the aspect ratio. Assuming the glider was thrown with the minimum thrust required, which is reasonable given that the glider is thrown smoothly and by not applying much force, the zero drag coefficient is approximately equal to the induced drag coefficient. By definition, the total drag coefficient is equal to the sum of the zero and induced drag coefficients. Thus, our glider's total drag coefficient is estimated to be 0.032. Here's a side-to-side view of our best test flight and the first competition flight. The iterative design process allowed for a significant improvement in flight performance, making the glider fly smoothly and break 60 feet in some flights. The trial and error process for finding the optimal location for the wings and ballast was key for enhancing stability and range. Our final design did meet the requirements. The glider fit in a 16 by 16 inch box, was built with balsa wood, and was only propelled and controlled by the throw. It flew more than 20 feet and had minor to no structural damages upon landing. In conclusion, we built a balsa glider with elliptical wings and stabilizers and followed an iterative design process by adjusting the location of the wings in the ballast to enhance its stability, meeting all design and performance requirements, and successfully flying more than 20 feet. Some areas of success include the stability of the glider and its reasonably long range. The most challenging part was the manufacturing process, and specifically achieving the desired dihedral angle. We learned how different design elements affect the glider's performance and gained insight about design trade-offs. However, there is still a lot of room for improvement for a glider. For instance, changing the dihedral wings to polyhedral wings could improve performance. Additionally, changing the ballast to shift the center of gravity closer to the quarter chord could make the glider fly even more stably. Sanding the winds to make the airfoil edges sharper could enhance the lift generation. Also, giving shape to the nose and rounding and streamlining the fuselage could achieve the same purpose. To enhance the precision of the final build, we could improve the wing and stabilizer alignment technique by using clamps or other supporting devices. Additionally, to reduce the glider's weight and thus improve its flight range, we could reduce the amount of ballast while keeping the same ratio between optimal locations. Finally, we could also add winglets to reduce the drag. Here's a list of our references.